Okay, so good evening, everyone, and welcome to today's Vancouver Kimberlite Cluster Seminar, and thanks for joining us. My name is Amy Maley, and I'm a master's student here at UBC, and I'm also this year's VKC host. I also have with me here virtually Maya Kobalova, who is our convener. The VKC is a series of seminars for diamond geology and related topics, and our goal is to bring academics and industry professionals together. I would like to acknowledge SRK Consulting for being a long-standing VKC sponsor. Just a few housekeeping notes for Zoom here. If you could please make sure that your microphones and your cameras are off, that would just ensure a good quality of streaming. And the presentation will be about 15 minutes long. So please keep your questions for the end, at which point I will help to facilitate a question and answer period. And then after the Q&A, we'll turn off the recording and then we'll have a bit more of an informal chat. And now I would like to introduce our speaker for today. So I'm happy to welcome Roy Bassoo Jr. as today's speaker. Roy is a geoscientist whose expertise covers a broad set of skills and experiences within both research and exploration. He is currently a postdoctoral researcher at the GIA, and he's involved in the study of diamond defects and how they manifest color. His research as a PhD student at Baylor University focused on diamond perigenesis, mantle geochemistry, and kimberlite volcanic processes using various geochemical, spectroscopic, and experimental petrology techniques. He has consulted as a geologist on various exploration projects concerned with locating and defining the prospectivity of gold and iron ore deposits. He has had the opportunity to manage exploration teams in remote locations in the Canadian Arctic, Amazon jungle, and West Africa. So welcome, Roy, and I will stop sharing my screen here so you can get started.
Okay, well, thank you, Amy, and good afternoon, everyone. Thank you very much for attending this talk, and special thanks to Maya Kobalova and VKC for allowing me to share my time with you. I'm honored, and today I'm going to talk to you about Guyana's diamonds, or specifically Guyanese diamonds. Being Guyanese myself, I grew up hearing about Guyanese diamonds deep in the Amazon jungle, and now as a postdoc at the Gemological Institute of America, I'm excited to share what I've learned about them and how they fit into the grander picture of the Guiana Shield and its evolution. Guyana's diamonds are also are ancient and rare minerals from the mantle, and they can persist in the sedimentary environment for a very, very long time. And they do preserve morphological and cathodoluminescence responses that speak to that. Guyana's gemstone mining industry, it's not fully developed, and there's definitely ample room for improved mechanization and recovery of other minerals aside from diamonds. So we'll just run into it. In case no one is aware, Guyana is situated on the northern tip of South America, nestled right between Venezuela and Suriname. Most of the population is concentrated here along the coast, but the bulk of gold and diamond mining occurs here in the highlands within the Amazon jungle, so away from the flatlands. It's English speaking, it's the only English speaking nation on the continent, and culturally, it's similar to Caribbean. So we can say we're culturally Caribbean, but it is a melting pot of many various different cultures from all over the world, and that are and throughout our history. And now we are distinctly Guyanese. We've had a long history of mining, especially diamond mining, with the first discovery in 1887. And as you can see, most of this region is covered by dense, thick, inaccessible jungle. And that's a problem, but it's also an opportunity. Any samples, rocks and minerals coming from this part of the world can help us, are rare, and they can also give us an opportunity to study the geology of the Guiana Shield. Now, beneath this tropical veneer is the Guiana Shield. And I won't go into too much detail about all the colors, but suffice to say that the Guiana Shield is composed of Paleoproterozoic arc terrains that accreted around Archean core complexes here and here. All the blues and purples and grays, felsic intrusive activity during the trans-Amazonian orogeny constitute most of the rocks that we observe within the Guiana Shield. And it's overlain unconformably by the Roraima Supergroup, with outlined here in light green, and these dark patches here, these black shapes. This is important. This is where the diamond story starts to get interesting. So I'm going to simplify things a bit. And so I've outlined here the Roraima Supergroup on top of the satellite photo of the Guiana Shield, at least the area. And the Roraima Supergroup is a thick, 2,300 meter thick sequence of sandstones and conglomerates that have been cross-cut by mafic dikes and sills. Many of them are tholeiitic, and it's aged between 1.7 and 1.9 billion years old. The Guyana Shield, the Roraima Supergroup, once covered more than a third of the Guyana Shield, and now it's just isolated here. Now, most of the diamonds, and if not all, most of the diamonds that we observe within the Guyana Shield are placer in origin. These big circles here are the major placer deposits. The only examples of primary deposits that we have in the Guyana Shield are here in Guanayamo in Venezuela from Neoproterozoic kimberlites, and here in Dachine in French Guyana from metamorphosed lampriphyres and lamprites. Now, it's thought that Guyana's diamonds are derived from the Roraima Supergroup rocks, given their proximity, especially along their eastern margin. But the same was also said from diamonds from Guanayamo, and we now know that to be untrue. Now, during the breakup of Gondwana and the opening of the Atlantic, tectonic uplift was followed by erosion and continuous surface evolution since that time. And it's led to complex placer deposits that host gold, diamond, and other gemstones. The Roraima Supergroup is then thought to be a sink for diamond deposits, but it certainly wasn't the most recent. Now, all these diamonds are found in alluvial deposits. We still don't know the exact source of the diamonds, of the rocks that host diamonds within the Roraima Supergroup. That's still an open question. But all the diamonds mined in Guyana are from alluvial and colluvial deposits. And they were first exploited by Porknockers. So artisanal mining in Guyana was born in the decades after the abolition of slavery in 1838. Many freed slaves sought a livelihood away from the sugar plantations and their former slave owners. Prospecting and hand mining for gold and diamonds in the jungle offered these once and formerly enslaved peoples both literal and metaphorical independence. They were called Porknockers because of their consumption of salted pork, which is easy to store and transport in the jungle. So Porknockers, that's where the term comes from. What we have here on the left is a stylized representation of one such Porknocker. And what this at the Guyana National Museum. And what this demonstrates is how little capital investment was needed to gain economic independence when you were formerly a slave. So to his right is a sluice box, which was called a Tommen box for filtering gold and diamonds from sediment. He also carries on his head a iron device. It's a conical shaped with a riffled interior. And this batel, as they call it, is used to pan for gold and diamonds and also protect the wearer from the sun. He also carries a cutlass or a machete to maneuver in the jungle, and cooking utensils, and also handmade wooden pipe for smoking tobacco, amongst other things. To the right of that photograph is a historical photograph of presumably the individual on which this sculpture was based on. If you notice, on his back is a basket, a woven basket made of palm fronds that was used to carry supplies. And they would search the jungle for diamonds like the ones here that we're showing in the video. So Porknockers would dig shafts up to 15 feet deep, sometimes timbered, sometimes not, to get access to these buried alluvial deposits. And they would also exploit stone lines or even shallowly buried alluvial and river channels, old paleo channels, for example. Now, porknocking, the term porknocker is an archaic term. Porknocking today is a small scale and independent to cooperative effort, and large groups of miners can form collectives and syndicates to mine for diamonds. Now, individual miners are sometimes paid a salary by claims owners, but in the jungle here, diamonds can be an alternative form of currency for purchasing fuel, services, and food, for example. Larger scale ventures rely on, heavy equipment borrowed from the gold industry. So placer deposits are excavated by an excavator. This is an example this is an example of one. And they're then pumped into a slurry or washed into a slurry by these high pressure hoses. And this slurry is then pumped to a sluice box and a jig to extract both gold and diamonds. And they're placed in a collecting pond. And then those minerals are then sieved and handpicked for diamonds, for other gemstones that we find in the area. Okay, now it's not very well publicized, but Guyana has contributed to the global supply of diamonds for more than 130 years. Their trade name has been British diamonds, hinting at their colonial past. In the 21st century, Guyana's declared production averages around 68,000 carats per year. And in 2004, had its highest production of more than 400,000 carats. So since then, there has been a steady decline in production, likely because of increasing gold prices. Guyana's diamonds are mined as an alternative to gold. So whenever gold prices are high, diamond production is low. Whenever gold prices are low, diamond production is high. And that likely explains the cyclical nature that we find. The average price per carat in Guyana for a diamond has been $175 roughly. So it's fairly profitable, and declared diamonds are taxed at a 3% royalty and a 2% withholding tax. Now, there is room for expansion and increased production, and marketing is one such area of growth. Since the 1990s, there's been a growing group of diamond manufacturing houses, most notably King's Jewelry in particular. That's one of the most prominent ones. And they polish beautiful set pieces like this. This is a 1 carat fancy brownish yellow diamond from Guyana. And yeah, it's still growing. There's still room for improvement, and also to get the word out that, hey, there are diamonds in Guyana, and they can be formed into beautiful pieces like this one. Now, we've covered the diamond industry, but what about the alluvial deposits themselves? So the alluvial deposits are medium to coarse-grained clast-supported sands with rounded quartzites and sub-angular to rounded igneous clasts. And these are buried. So this is where it's outlined here. And these are buried usually by thick sequences of fine aeolian sands. And these deposits host not only diamonds, but gold, rubies, sapphires, topaz, rutile, garnet, chromite throughout Guyana. And another useful mineral is detrital zircon. So we sampled alluvial and colluvial deposits in the Kurapung area, which is the major diamond center there in Guyana, the major deposit where most of the diamonds come from. And we were able to do detrital zircon, uranium-lead geochronology on these deposits. And what we found is a unimodal peak at around 2.1 billion years old. What's interesting about this is that it corresponds to the age of the trans-Amazonian orogeny. So we infer that rocks from the trans-Amazonian orogeny are constituting the zircons within these alluvial deposits. Also interesting is that none of these groups are represented in the Roraima formation or the Roraima Supergroup H, nor are there any groups from West African kimberlites or Guanayamo kimberlites. And that's interesting. That's interesting because it can suggest that we have rocks within the Guiana Shield that are hosting diamonds currently, or they've been weathered. The Roraima Supergroup is now holding or hosting rocks weathered from the trans-Amazonian orogeny that now host these diamonds. So now that we've talked about the alluvial deposits, let's talk about the diamonds themselves. Most of the diamonds are colorless, but Guyana is known for green skins and green body diamonds. We also find yellow colored diamonds or even very rare white bodied diamonds. Guyana's diamonds are usually small, but up to 10 carats have been found. The largest stone ever recovered has been 56 carats in the early 20th century. But you do find examples like this large fellow right here, which is about a 6 carat, and it's got a faint greenish body color. And yeah, we do find them from time to time. When we talk about morphology, dissolution textures are prevalent in 95% of the diamonds. Most of the diamonds in Guyana are octahedral to dodecahedral, but we do find flattened and cubic forms as well. Of particular interest to me are these flat bottom textures here, like these flat bottom trigons and these flat bottom hexagons and these microdiscs and microdisc swarms. It might be a bit difficult to appreciate, but there's quite a number of these microdiscs here. Now, experimental work by Fedorchuk and her lab in Dalhousie, they've demonstrated that defects, look, dissolution pits on diamonds begin as point bottom features. But when you have a diamond in a more H2O rich than CO2 rich fluid phase, they tend to dissolve more rapidly in the lateral direction rather than the 1-1-1 direction. What ends up happening is that it creates these broad, flat bottom textures in these diamonds. And in their work, they've only been able to produce microdisc features using a very saturated fluid-rich phase of water. That's interesting because 70% of the dissolution textures that we observe within Guyana's diamonds are these flat bottom textures and these microdisc swarms, for example. That tells us that whatever hosted these diamonds, whatever entrained these diamonds and brought them to the mantle was likely very water rich. Now, it could be a water rich kimberlite. That's not unheard of. We do see that in Ekati in northern Canada, or it could be more traditionally a lamproite, which typically has a higher water content, or lamproites, so to speak. Okay, when we consider another morphological characteristic, which is interesting to me. Oh, let's go back. Sorry about that. 85% of Guyana's diamonds have some form of abrasion. So whether it be percussive marks, edge abrasions, scratches, and 85% of them have some degree of abrasion, from very light abrasion to completely abraded in this example here, which looks like a sand grain, for example. Curiously, so that's interpreted to mean that these diamonds have been entrained and involved in various episodes of erosion and deposition from their original host rocks. Now, this is interesting because diamonds are very hard and they persist for a very long time. And it takes billions of years to incur these abrasive textures. So that's very difficult to do in a natural setting, unless there's special circumstances. 15%, however, 15% of the diamonds we observe in the same population are pristine diamonds without any abrasive textures whatsoever. So we're talking zero. And 50% of the population display this characteristic. So now how can this be if both the diamonds are extracted from the same alluvial deposit? Optical spectroscopy can shed some light on this. Now, diamonds are composed of carbon, that's no news there, but impurities such as nitrogen are common, as are the associated defects, which manifest a cathodoluminescence response. Now, it's important here.
You don't necessarily want to reiterate the results.
Hello? I'm sorry, I thought I heard a feedback. Okay, a distinction should be made here between cathodoluminescence and UV luminescence. Cathodoluminescence, of course, requires high bombardment by high energy electrons, around 50 kiloelectron volts, whereas UV luminescence is a result from bombardment by photons, which have between 1 to 5 electron volts in terms of energy. That means is that when we bombard a diamond with cathodoluminescence, or analyze a diamond through cathodoluminescence, we might be exploiting or exciting particular defects that require higher energies. Okay, so worldwide, diamonds from unmetamorphosed deposits, primary deposits like kimberlites, cathodoluminesce blue. And the blue luminescence is attributed to the N3 defect, consisting of 3 nitrogen atoms surrounding a vacancy. What's curious about this, and this has been demonstrated experimentally, is that changes in temperature can actually alter that defect. So the vacancies and interstitials become more mobile, and they migrate throughout the crystal lattice of the diamond to form new optical centers. Those new optical centers result in a higher wavelength away from blue to other colors like greens and reds and oranges, as an example. And we do find that in natural systems. In fact, in burial in sedimentary rocks can produce resonance temperatures of 50 to 250 degrees, and even rarely 350 degrees. And because we know that the abraded diamonds in particular, in Guyana's diamonds, let's say they're derived from this Roraima Supergroup, they can reside in that sedimentary system for billions of years. So the abraded population of Guyana's diamonds, 19% of them, a smaller percentage, cathodoluminesce blue, whereas the non-abraded population, cathodoluminesce, more than 55% of that population cathodoluminesce blue. That could mean that this abraded population here has experienced a higher degree or more of that thermal change than the non-abraded population. So it's not just that you have these two populations. These two populations also demonstrate different spectroscopic or optical spectroscopic responses. So in summary, now it could also mean that these non-abraded diamonds are probably coming from an unmetamorphosed type of rock. Whether that's a kimberlite is up for debate, but it could be perhaps a rock that hasn't been as metamorphosed as the ones that are hosting the abraded population. What I'd like to point out here is that these thermal changes that lead to these changes in optical spectroscopy, these defect and interstitial changes, might be a useful exploration tool where we can examine a suite of diamonds from a region and then examine their morphology and also their cathodoluminescence response. Because here we do see these differences. Guyana's diamonds are also composed, the most abundant impurity in diamond is of course nitrogen, and this is the population of nitrogen types that we observe throughout them, the entire set. Most of them are type 1A, ABs, but we do run small examples, about almost 70% of type 2s, and then everything in between. What's interesting here is if you take that, we measured these by FTIR, by the way. If you take the total nitrogen content and plot that against the nitrogen aggregation, so going from simple nitrogen forms like nitrogen pairs, all the way to more complex aggregates, you're able to calculate or derive a residence temperature. So we assumed a residence time of about 3 billion years, assuming they're derived from the Roraima Supergroup, which we do know the age of. And we see, again, the abraded and the non-abraded diamond populations fall into two broad groups. Now, I'll admit there is some overlap, but we do have some that seem to form along a cooler resonance temperature rather than the abraded diamond population, which seems to span the entire range. Now, this is not terribly exciting, but it does tell us that these diamonds are cratonic. So they are from the cool cratonic route. If we grind the diamonds into a powder and then vaporize them to CO2 gas for mass spectrometry, we're able to measure the delta carbon 13 ratio, or the ratio of this isotope in particular, delta carbon 13. And we find that this ratio falls between -3 to about -15. But what's important here is that the bulk of them form within what we would expect for peridolitic type mantle. So most of Guyana's diamonds are from the peridolitic type mantle with a smaller population of eclogitic type rocks. Now, when you go past -15, you start heading into websteritic type mantle rock territory. And Guyana's diamonds are different from the sheen diamonds overall. The sheen diamonds seem to be very negative in delta 13. And Guanayamo diamonds overall are more eclogitic in nature. But Guyana's diamonds are also very similar to those we would expect from Brazil, for example. So in a general sense, we have an idea of where these diamonds crystallize from, what type of rock, but geochemistry can tell us a lot more. So to figure this out, you need to get at the diamonds. So at Baylor, we acquired a metal skife running at 3,500 RPM, and we were able to polish and expose inclusions like these here. So these are chromites and olivines and orthopyroxenes set within a particular diamond. This is a stacked image. And the inclusion suites that we find within Guyana's diamonds are chromium, pyro, forsterite, enstatite, and chromite dominantly. We do find some examples of rutile, clinopyroxene, but the majority of the diamonds, 20% or under 20% of the diamonds that have inclusions, the majority of them would be either forsterite or enstatite or chromite, chromium pyro. So again, this is evidence that these diamonds are coming from dominantly peridolitic type mantle rocks. One other thing we can do is use Raman spectroscopy to estimate formation depth. Raman spectroscopy is a very powerful tool. The shape and position of Raman spectra are a consequence of the mineral's crystal lattice. And minerals that are entrapped within a diamond, which is very rigid, will be under stress. And the peak position of their Raman spectra will change with stress. And that has been calibrated to calculate residual pressures in both olivine and garnets hosted within diamond. So we are able to derive residence temperatures, not just for the foresterites, but also for the chromium pyropes. And you can see most of them fall between about 5.3 to 7 gigapascals, which places us at about 170 to 220 kilometers, which is right at the base of the craton. And if that probably falls in geotherms between 40 and 35, similar to the Siberian craton and maybe even the Kapval. You will notice a few or a handful of these inclusions also plot above the graphite to diamond transition, not claiming that these are forming in that environment, but what these are likely representing are examples of inclusions that have been relaxed. So the minimum values of these are most representative of their entrapment pressure, so to speak. Now, we also estimated the formation conditions of chromium pyrope using traditional geothermobarometric methods, the chromium barometer and the manganese thermometer for chromium pyrope. And so you can see they form within the similar range. So it sort of validates what we've estimated from Raman thermobarometry. Okay, geochemically speaking, the inclusions that we examined by electron microprobe are elevated in chromium, aluminum, magnesium, and they're low in calcium. This is consistent with a moderately depleted harzburgitic paragenesis. And so this is, again, lending evidence this whole harzburgitic peridotite type mantle rock from which these diamonds are formed. Most of the diamonds that we observe, most of the cratonic diamonds are derived from this particular rock, harzburgite in particular. When compared, if we look here with the garnet inclusions, when compared to the garnet inclusions from Guanayamo diamonds, you can see that ours from Guyana are more peridotitic in nature. There are higher chromium content, except for these here, but most of the inclusions we find, the garnet inclusions that we find within Guanayamo are eclogitic. Okay, now these inclusions also record evidence of metasomatism. So manganese is a proven indicator of metasomatic alteration in olivine in particular. So one would expect fertile mantle, lurzolytic mantle to have a high magnesium content and a low manganese, placing us here. Now we don't have any examples of this, but perhaps this is an example of the refractory mantle of the Guiana Shield, which we are not sampling. Following partial melting, that magnesium content would decrease, but the manganese content would increase. And we would follow a metasomatic trend by alteration by fluids if we have this particular trend here. But if we interact with melt or rock, it would push to higher manganese values. So these are examples of our forsteritic inclusions here, and our enstatite inclusions here. So we fall along a metasomatic type of trend, or a metasomatic type of profile. What this means is that Guyana's diamonds are forming from already depleted mantle rock, probably following some ancient depletion event that likely preceded diamond crystallization. So we know that this is not entirely unheard of. Schultz et al. In 1996 did some XRT work of metasomatic veins of diamonds hosted in eclogite, and indeed, these diamonds are spatially associated with these metasomatic type veins. So now let's talk about the big picture. These fluids are altering mantle rock. The diamonds are entrapping these inclusions of olivine and in the cratonic root. And olivine is, of course, the bulk mineral of the mantle. Now, what can we say about the fluids that are participating in this particular event, or these events? Lattice-bound hydrogen occurs in nominally anhydrous minerals like olivine, and they can occur bonded to hydrogen and oxygen. And we can use FTIR to measure their water content. So we polished the Guyana's diamonds into plates, parallel plates, one on either side, so that we can have the inclusion suspended, I guess, between these two plates. And we were able to acquire infrared spectra from these inclusions hosted within the diamonds. And they have some absorbance within the OH region that we expect for olivine. And so this is the integrated area of these examples of spectra. And you can see that forsterite has a lattice-bound hydrogen, what we'll call water or ppm water by weight, between 8 and 160 ppm. And enstatite has between 2 and 104, so slightly lower. And we used the Beer-Lambert law and known calibration coefficients to estimate this water content. Now, if we plot that water content with formation depth from Raman thermobarometry, we find something interesting. We find that Guyana's diamonds are within the range expected for other peridotite xenoliths from the Siberian, Kapval, Tanzanian, slave craton. So that's interesting. They are, however, wetter, I guess you could say, than Siberian inclusions, which is interesting. Now, so these samples may be representative of the cratonic mantle, and they are wetter than the Siberian craton. But why is that? Why is this possible? Olivine inclusions, we know, from the Siberian craton in those diamonds have lower phosphoritic content, higher phosphoritic content, lower manganese, and lower water content, possibly because the diamonds are entrapping olivines in less depleted mantle rocks. And we did see that Guyana's diamond inclusions, the olivines in particular, do record some sort of metasomatic alteration. So we have these diamonds forming within the cratonic root, and it's seemingly relatively dry, and it's likely forming, therefore, in a highly reducing environment. So what I'm presenting to you is probably the first, as far as I'm aware that we know of estimating iron 3 to iron 2 ratios or oxygen fugacity on chromite inclusions from diamonds in situ within diamonds. The iron 3 to iron 2 ratios within these chromites were calculated by charge balance, adjusted to a calibration curve created by an internal set of standards with known iron 3 to iron 2 values derived from Mossbauer spectroscopy. And we used the calibration of Ballhaus et al. In 1990 to calculate the oxygen fugacity relative to FMQ, or the Fayolite magnetite quartz buffer. What this shows us is that Guyana's diamonds inclusions, the chromites in particular, average about 1.6 and range between -1 to -4. So that's it's similar in range, or similar to that from kimberlite mantle xenoliths from the slave craton, and slightly reduced from the Kapval and the Siberian craton, which is interesting. Now, let's talk about that for a minute. They're existing in the cratonic root, but it's in a highly reduced environment. How is it that you can have inputs from subducted crust, for example, to bring this carbon in, for example, and how can you maintain this, this highly reduced environment? Surely the oxygen fugacity must go up. This suggests that there must be some sort of buffering going on here, and perhaps it's buffering from fluids directly from lower sources in the mantle. And it disfavors a meteoric or meteoric hydrogen source. Now, strong contenders for lattice bond hydrogen in these reducing conditions might be methane, it might be hydrogen, or it might be hydrogen sulfide fluids degassing from the lower mantle. This is not entirely unprecedented because we know that the most abundant inclusion within diamond globally are sulfides. Those are the most abundant inclusions that we know of. So it's quite possible that this is the fluid or the fluid phase that's involved in the precipitation, or at least in the metasomatic alteration of mantle rocks. And we also know that with decreasing oxygen fugacity and increasing depth, the solubility of sulfides in the upper mantle increases. So what I'm saying here is that this result could imply that there's an unaccounted for hydrogen within the total budget of the mantle. Okay, so that's going in a bit too much detail, but so this is the general picture. We have the cratonic root, diamonds forming within the cratonic root at one particular time, fluid metasomatism infiltrating here, more diamonds precipitating, and eventually along this line, kimberlites erupt, entrain these diamonds, and bring them to the surface. And depending on at what age or what time they erupted, they may determine the type of diamonds that we're able to sample, and also the type of inclusions that these diamonds are able to sample. Okay, so in summary, big summary, Guyana's diamonds typically cratonic, harspergitic pyrogenesis, and their inclusions can tell us a lot about the cratonic root of the Guiana Shield, which for the most part has been a large unknown. Most of the data we know is from the western portion of the Guiana Shield, but in comparison, we do see there's some heterogeneity even within the cratonic route, from the western portion of the Guiana Shield to the central portion where Guyana is located. I do suggest that combined cathodoluminescence and morphology of diamonds might be a useful exploration tool, especially in megaplacer terrains when we have mixed populations of diamonds from primary source rocks and then secondary source rocks and then secondary source rocks, for example. On a final note, Guyana's gemstone industry is in its infancy. There's definitely room for improved mechanization and recovery of diamonds. And we do find examples of corundum. So these are rubies, well, not rubies and sapphires, but corundum of various colors. And we do find topaz, and many topazes also have this blue tint or blue haze to them, but you do find other examples like browns and greens, for example. So yeah, I think that's it for me, but I wanted to thank you all very much for listening, and I would love to hear your questions or to answer anything further. Thank you.
Thank you, Roy. That was really interesting. It looks like we have, oh, I don't think that was meant for everyone in the chat. So if anyone has any questions, you can send them to me through the chat, or you can just go ahead and ask them to Roy right now. I'll ask one quickly. Was this part of your PhD research, or is this what you're working on right now at GIA?
Can you hear me?
Yeah.
Yeah, this was part of my PhD research.
Okay.
The part that's related to GIA is the fact that we do have green diamonds with a known geographic location. The green diamond issue has been one that's been plaguing the diamond industry for a long time. And I'm hoping I can put my 2 cents into it. But yeah, it is a spin-off because we have green diamonds, green body diamonds, green skin diamonds with known geographic locations, which is important. Provenance is a real game changer when it comes to things like that.
If I may follow on the same thing that you started describing, those green diamonds and green skin diamonds. So seems like they're coming from geographically restricted area. Is it right? Like you mentioned that you have it from Guyana, but you also have them from Brazil. Is it just that part of South America that they are restricted to?
No, actually, I think I've heard of or read of one in Russia as well. And it seems if you cross-section that entire kimberlite pipe that hosts, I can't remember the name of it, you probably do, but if you cross-section that entire pipe, you do find green diamonds associated with the lateritic weathered portion of that kimberlite pipe, which is green diamonds in particular, which is interesting. So Brazil and Guyana that I know, the tropical weathering profile allows for the formation of laterite, and laterite may play a role in the preservation or manifestation of these green diamonds.
It looks like we have a question in the chat here from Brooke. He is asking, what kind of exploration work did you do in Guyana?
So actually, yeah, that's a good question, because I did not do any or much exploration work for diamonds in Guyana. A lot of that I learned while doing my PhD. But prior to that, I was a consulting geologist for a gold exploration company. So mostly epithermal or lode gold systems. I was also an exploration geologist in northern Canada for iron ore. But the bulk of my time in Guyana was spent looking for gold.
Does anyone else have anything to ask?
I would like, Roy, to ask you again. You mentioned an interesting training program that GIA is now setting up in Guyana to educate the artisanal miners. Can you tell us more about what
Yes.
GIA is planning to do there?
Yeah, absolutely. Okay, so we know that diamond brokers get the lion's share of profits when in environments like this, especially with artisanal miners who are usually ill-informed of exactly where rough diamonds and how rough diamonds are manufactured or along that chain. So GIA has done something similar for colored stones in East Africa, where they prepared an artisanal miner's handbook. And I can send you the link for that, actually. But what it does is they go out and they talk to local miners, and they form this program or sort of trains them. Okay, how do you look at colored stones to ascertain their value and how they can be cut, what type of value, what can be cut, what cannot, what colors are valuable, what colors are not, what sizes are valuable. So if we take that model and we apply it to diamonds, the metric in Guyana for diamonds from artisanal miners is weight. They're just sold by weight. But there's so many other nuances about what's cuttable, what's not, the colors, and miners aren't informed about that. So GIA, and they've sort of drafted me into that as well, they're planning to do some similar program in Guyana, because Guyana is English speaking, it's right nearby, and I know the ground. And we're hoping to do something similar in that respect. We're hoping to inform and educate local miners and using Guyana as a test ground about diamonds and how diamonds are manufactured, so that when the idea is that when a local miner has a parcel of diamonds, he can sort through them and then start to isolate which ones are more valuable than others based not just on carat weight. And we're going to use the feedback from this initiative to develop a artisanal diamond miner's handbook in various languages.
Doesn't look like we have.
Roy, I'd like to ask you a question. I missed almost all of your talk because I just couldn't get a stable connection from Calgary. But I'm wondering, the only slide I saw was the one where you had actually rupees and sapphires and topaz. Is it normal to find those gemstones along with diamonds? And what are the, if you actually talked about that in your talk, I can listen to the recorded.
Oh no, I am happy to talk about gemstones and diamonds for hours. So thank you for the question. Yes, it is. So it is quite common to find those. Yeah.
And I'm just wondering, what's the chemistry that makes those? I mean, okay, so those were found, but were they found coming from the same ore body?
So we don't know. We don't know. We know that.
Oh, these are alluvial.
These are all alluvials, yes.
Okay, they're alluvial gems. Yep. That were all found in some sort of. Oh, I see. So well, in fact, do you actually see those together? Do you see any of those three gemstones along with diamonds ever? Is that something that's known in other parts of the world?
Yeah, I'm not sure. I'm actually not sure, but I do know that the Guiana Shield during the Trans-Amazonian orogeny, we've got voluminous amounts of felsic granites and pegmatites and so on. So I don't think it's completely out of the question for topaz. For the sapphires and the rubies, I'm not very familiar with it, but I have heard that perhaps we are looking maybe at lamprifiers, for example, as like we do in Montana and Yogo Gulch.
Mm-hmm.
May I comment? Suzanne, you asked about other parts of the world where that association is known, and we see the same thing in Wawa metaconglomerates. So that's Archean metaconglomerate in the Superior Craton, Northern Ontario, and diamondiferous conglomerate, but also it collects all high density minerals like emerald, like sapphire, like ruby, gold. So if you can get that high density concentrate from that conglomerate, so it will bring you an amazing suite of gem minerals, including diamonds.
Right. it'd be a really nice, a nice rich deposit you'd be stepping, finding if you could find those gemstones all together. And
yeah, and it's been like this for about 130 years with little mechanization and little, and there's still a lot of room and a lot of work to be done.
It looks like Howard had a little bit of information that he posted into the chat too about your question, Suzanne. I don't know, Howard, you want to elaborate on that a little bit too?
So yeah, I actually have an interesting story about this Golden Star report. Amongst so the regulatory body in Guyana is called the GGMC, or the Guyana Geology and Mines Commission. And it's a semi-private, semi-public institution. And yes, they do talk about the Golden Star report. But if you try to find this Golden Star report to actually look at the data or to see it, it's very difficult to come by. I myself have not been able to acquire it. If you have it, Mr. Cooper Smith, I'd love to get a copy.
Okay.
People claim at the GGMC and within the group, they claim, oh yeah, it exists. And the impression I get is you have to be in the know, or pay, somebody somewhere is hoarding these reports, and maybe they're behind the scenes discussing it with other people.
This is Howard. I would mention that I've seen the reports and I've seen the rocks as well that Golden Star found. Hard to say exactly what they were, but and I've seen the minerals that have come out of them and the diamonds. On the Venezuela side, those were my observations looking at, in various placer workings and different drainages where you saw very different diamonds coming from almost adjacent drainages.
Interesting. So you're saying that there are kimberlites here ready to be, or at least some sort of diamond-bearing igneous rock ready to be, got on there.
There are things to look for and look at, yes. Nothing appeared even close to economic, but I mean, those very preliminary discoveries at that point.
That's very exciting.
All right, does anyone else have anything else to ask? No.
Well, actually, I have a comment. Did anyone see JLo's green diamond engagement ring?
I did. That was the first thing I thought of when you showed those green diamonds. They're going to become even more popular now.
It's a hot topic.
Okay, well, I'm going to go ahead and stop the recording now.